Last time we had to miss the class. In fact, I had to miss the class. I was terribly sick by this time last week. So I had to go to the doctor. And then because of that reason, we had to miss it. But it happened for the first time for you probably in the second day, but uh, in last 10 years, that was the first time I had to cancel a class due to sickness. Okay. So we can start real number system today. Algebraic part, the like basic algebra is almost done. So we can start real number system. Here we basically see how it's evolved from the very basic set of numbers. Because this is in the syllabus at the beginning, but there won't be any questions from this, right? However, even though there are no questions from this section, you need to be familiar with certain notations, right? And don't misunderstand. I mean, don't misunderstand. Like you are not being asked to explain notation. So identify a notation, but in a problem, the notation is given. So you need to identify what it is, right? So initially, this is the number system they had. Our ancestors had this number system. I mean, the set of numbers up to 10, the numbers that they used by counting using fingers. Then, by employing various mathematical operations, this was extended. That's what happened. Certain new numbers were introduced to the current system. I mean, to the system that they knew at that time. Right? For example, the very basic, if you take addition, like if you take 5 plus 3, which is 8, it's in the set. But if you add 9 plus 2, it's a new number. It's a new number, right? Or if you try to add something like this, you choose two numbers from this set and add them, you get 12. It's also new. So by doing so, this was extended to this set. 1, 2, 3, all the way up to infinity. Usually these denoted by natural numbers these called natural numbers, a set of natural numbers, and it's denoted by n. However, in A levels, we usually don't use this notation. Right? I'll come up with a new notation. Soon after, I'll explain the next step. Now, when we use subtraction, you can choose numbers from this set, like 7 minus 4, which is 3. It is in this set. 6 minus 6, 0. It is not in the set. And then if you take possibly 8 minus 9, it is minus 1. It is also not in the set. Therefore, some new numbers were added to the system. And finally, they had this set. Minus infinity to all the way up to plus infinity, but we know only the integers. This is called the set of integers. I could have pushed this line. So let me do it. Integers. Integers are denoted by, the set of integers are denoted by this. Now this, you can identify this one as set of positive integers. Either you can call them as natural numbers because you use them to count 1, 2, 3, 4, or you can call them as positive integers. Therefore, since this is used to denote the integers, instead of Z, instead of N, you can use this notation to denote positive integers, Z plus. Now that's also done, right? After that, they used multiplication. But if you multiply two integers, you always get an integer. Therefore, new numbers were not added via multiplication. Now they used division. When you use division, there were three types of numbers came up. First type is the integers itself. Like you can divide numbers like this. Which is 2, 14 over 2, which is 7. Even though you divide two numbers, you get a whole number. So integers. Oh, you can say no decimals. There are no decimals here. Now the second type is like when you have these type of numbers. Here you can see that the denominator always contains numbers which has factors 5 and 2. Here the prime factors are 5 and 2, 5, 2, because this is 20 squared. The factors in 20 are 2s and 5s. Here, 2 to the power 6, 2 to the power 8. Here it is 5 to the power 1. Now, if you look at the decimal form, you have it like this. Here you have it like this. Right? Sorry, I forgot the equal sign. Here it is 0.056. Now look, here you have decimals, but decimals are finite. They are only finite decimals. Right? Finite decimals. Then the third type, where you have something which is not 2 and 5. To divide it, you get that one. Here it repeats. The smallest repeating chunk has only one digit. Therefore, you can put a bar on top of that. That means it is 0.333. After that, it repeats. 2/7. You can write this as the smallest, the largest repeating chunk is this. So if you have something like this is a longer one, no? Compared to the previous one. Right. So that's a repeating chunk. Now here we have infinite decimals. But there's a period there. Oh, I'd say there's a pattern or repetition. So these are called rational numbers. There's a ratio. So we got the extension like this, huh? Let me do it somewhere here. You had the set A. Then we extended it to the positive integers. Then we have subtraction, we extended that to Z. Then using division, we extended this to the rational numbers. I'm sorry, I forgot to write that notation. In the case of rational numbers, the notation is this. Q, script Q, quotient. Now, something is still missing. What are those? I mean, one class is missing. What are those? Here you have no decimals, numbers with no decimals, numbers with finite decimals, numbers with infinite decimals. So what's missing? You can have infinite decimals with with no pattern. These are the numbers of that sort. Like if you have a ratio of integers, either you can have no decimals or finite decimals. The third type is infinite decimals with pattern, with repetition. Right? However, one type is missing. That is the numbers where you have infinite decimals. But if you write 1 million of decimals, next one cannot be determined. Next one is unknown. ඊගාව එක මොකක්ද කියලා කියන්න බෑ. 10ක් ලිව්වොත් බෑ, 100ක් ලිව්වොත් බෑ, next weekend. We don't know what the next one is. So some examples are like this. Sorry. It goes on and on, but there's no pattern. There's no pattern. There's no pattern. Even though you find thousands of numbers, the next one cannot be determined like that. There's no pattern. So these are called irrational numbers. Now, these are not rational numbers. If you write a ratio, then always you have the decimal sequence in this way, either finite or infinite with repetition. So if you now, these are different class. Set of irrational numbers are denoted by P. They are from different class. Like say, for example, if you take 5, it is here. If you take -2 is here because it's not an integer, but positive integer, but it's still an integer. If you have 3/2, it is here. However, the irrational numbers are not in this set. It's a different set. This is the set P. So if you combine both of them, if you combine both sets, you get the set of real numbers. So R is P union Q. If you combine both rational and irrational numbers, you will end up with this irrational. You get R. So this is R. But there are some other notations like this. Say if you get the full real line, that is R. But if you say 0 is here, if you get all positive reals, you write it as R plus. Similarly, if you have 0 together with this, means non-negative integers like 0 and all positive numbers, it is R0 plus. And the notation is consistent with Z as well. Now, if you take this set, Z. But if you take all positive, like this, if you take all positive integers, that is Z plus. But if you include 0 in there, you get that. So the notation is pretty consistent, but these are for reals, these are for integers, right? Okay, you take that down. All right. We'll start the section from which you get questions. Now, if I have to summarize this now, combined math comprises both pure and applied. This one has 2 papers as well as the applied. Here you get 10 questions. In pure, you get, in the second paper, you get 7 questions. In part B of problem 11, that part is from remainder theorem. So we'll start that part. So if you take polynomials, I'll come up with some examples. Before that, I have to give the general form, but general form cannot be obtained without actually looking at examples, right? There are some definitions involved with these polynomials. Those are leading term, the leading coefficient, then you have degree. So there are several examples. I'll come up with some examples. A polynomial is something like this kind of a table. No? Now, polynomial is a combination of such terms where you have non-negative powers of x. All these are polynomials. All these are examples for polynomials. Now, leading term is the term which carries the highest power of x. Right? Now, if you take this polynomial, this is the leading term which carries the highest power of x. Right? Now, if you take this one, this is the term carrying the highest power, x cube. That's called the leading term. Here, the term carrying the highest power of x is x squared. In the fourth one, you have to consider it together with minus sign, minus 4x squared. Here, this is the term carrying the highest power because here you have x to the power 0. So 7x. Here you have 4. You can consider 4 as 4 times x to the power 0. So this is 4. Now the leading coefficient is this. If you look at the leading term, there are two integers, so two numbers. Look, 6, 4. Here it is 1, 1, 3. Even though 1 is not explicitly expressed there, 1 is there, 1, 2. Now the leading coefficient is the term sitting in front, the number sitting in front of these terms. Like here it is 6. Here the leading term is 1. Even though we don't explicitly write it, it is 1. Here also it is 1. Here the leading coefficient is -4. This one. Leading coefficient 7. If you identify this as 4 times x to the power 0, the leading coefficient is 4. However, the degree is the most important thing. Degree is the power appearing up there. So here the degree is 4 because that defines the entire properties of this polynomial. For the time being, we don't have much to do with that. However, degree is very important when it comes to the polynomials because the shape of the polynomial or the behavior or the different traits of the polynomial are defined by that degree, the power. Usually when it is 2, you call it as a quadratic equation, quadratic function. When it's a 3, you call it as a cubic function, like that. So this is when you have 4 cubic function or cubic polynomial, here it is quadratic polynomial. When you have first power, it's a kind of a linear polynomial. It's a constant polynomial. Everything happens based on the degree of the polynomial. So degree is the most important thing. Let me put asterisk there. So degree is simply this highest power. It is 4. It is 3. In this case, the degree is 2. Here the degree is 2. Look, the highest power appearing in the polynomial is the degree, 2. Here it is 1. So it is 2, 1. In the last case, there's only one term, and the power corresponding to that is 0. So here 0 degree polynomial. Right? Now, those are some definitions pertaining to polynomials. Now, I promised you to write the general form. General form is like this. Now, if you have something like this, you can see the starting point cannot be determined straight away. Degree can be anything. So let's write a polynomial of degree n. So you have x to the power n. Then you can have something like this. Here, to avoid any confusion, I'll take this coefficient as an. So an goes hand in hand with this x to the power n. This an minus 1, this a2, this a1, this a0. A0 goes with x to the power 0, but we don't write x to the power 0 explicitly. Right. So that's the general form. Here, the degree of the polynomial is n. Right. Now, after looking into this general form and examples, definitions, we can understand the similarity between polynomials and integers. And at the first place, you need to know why we learn this. Usually, when we go to school for the first time, we deal with numbers. We add them, like 7 plus 2, 11 plus 13, those type of stuff. So similarly, polynomials are exactly polynomials have the same algebraic structure as integers, right? So we see the comparison. Right. Now, this is similarity. Let's take 4 basic mathematical operations. Addition. So we let them like add 2 integers. So on the other hand, I take similar polynomials, like I take 3x plus 4 plus 4x plus 2. You can see that 34 goes hand in hand with this one. 42 goes hand in hand with that 42, 3, 4, like that. So here when you add them, 4 plus 2 is 6, 3 plus 4 is 7. Here, when you add similar terms, 4 plus 2 is 6, so 3x plus 4x is 7x. You can see that this is 76, this is 76. Subtraction. Right. So when you subtract numbers, I'll write the similar polynomials. Look, 87 minus 62. 7 minus 2 is 5. 8 minus 6 is 2. Here, 8x minus 6x, 2x. 7 minus 2 is 5. Now we can multiply. But if you may go down to somewhere here. Anyway, I can do the multiplication. So we'll multiply something like this. Huh? Can you take something to the video if I write somewhere here? Right. Now, when you multiply this by 1, you get 112. When you multiply this by 3, you get 336. When you multiply this by 1, you get 112. When you add them, you get 2, 7, 1, 3, 2 is 6. This is 4, this is 1. Now we'll do a similar multiplication. This times x squared plus 3x plus 1. You can see that 112, this 112, this is 131, this 131. Now let's multiply x squared times x squared, x to the power 4. X squared times 3x, 3x square cube. X squared times 1, x squared. Now multiply these two. X times x squared, x cube. X times 3x. You get 3x squared. X times 1, x. Now 2 times. 2 times x squared. 2 times 3x, 6x. 2 times 1, 2. Now when you add them up, you get x to the power 4 is 4x cube. This is 1 plus 3 plus 2, 6x squared. is 7x plus 2. You can see the similarity. 14672. 14672. And how this is formed is 6 is obtained by 1 plus 3 plus 2. Here, 6 is obtained by 1 plus 3 plus 2 by adding 1 plus 3 plus 2. Okay. Now the last one, which is division. So in this case, we take this particular example. Right. So what we do is that you perform the division, but let me do it like this. You first take this down up to this point. Then I'll do this for you. Okay, I'll do this later. First, you take this down up to this point. When I see this from the outside, I felt like it should have been better if I do it like this. Reduction. And this is the general form of a polynomial, not something else. Right. Should be in that way. It should be, it should easy to follow. I mean, you can easily follow it if it is in this way. So we basically talk about polynomials here. In the second chapter, we go through the remainder theorem. Right. Now, we looked at the similarity when we operate polynomials and numbers via addition, subtraction, and multiplication. Now we are going to look at the division. That's the most important thing. In A levels, after that, we don't go through these things. We basically concentrate on the division only, right? Okay. Now let's consider the integer division. There are 112, there's only 112 for this 13. So 1 times 12 is 12. So when you subtract, you get 1. Bring this 5 down to this place. For 15, there's only 112. So 1 times 12, which is 3. Bring this 8 down to this place. So when 38 and 12 is, there are 3 12s for 38. Therefore, write 3 up there. 3 times this, 36. So the remainder is 2. You can write the answer like this. 1358 divided by 12. It's an improper fraction. Answer is 113. And the remainder is 2. Usually this is how you write the improper fraction like a mixed fraction. However, if you multiply this by 12, you will end up with this. Right? This is gone. When you multiply this by 12, you get 100. 12 times 113. When you multiply this by 12, you get 2. Now let's consider the division of polynomials. I'll take the similar polynomial. You can see that here the numbers are like 1, 3, 5, 8. Here also the numbers are like that. Here it is 1, 2. In x plus 2, you have coefficients like 1 and 2. Now, when you divide polynomials, this is how you do it. You take the leading terms, divide the leading terms, right? For example, when you divide this one, like x, divide x cube by x, like that. You get x squared. Now, x squared times this, x cube, x squared times 2, 2x squared. You subtract this 0, this is x squared. Bring this 5x here. Now, with the remaining part, this is the leading term, x squared. Divide x squared by x. You get x. Now, with this x, you multiply x times x, x squared, x times 2, 2x. Now, subtract 0, this is 3x. Bring this 8 down. Now, for this one, this is the leading term, 3x. Divide 3x by x. You get 3. Now, multiply 3 times x, 3x. 3 times 2, 6. Remainder is 2. Look at the similarity. 38 minus 36 is 2. Here 3, 8, 3, 6, 2. They are similar, right? Now we'll write it as like usual division. Is equal to this guy plus 2 is the remainder. This is the divisor. Now you multiply everything by x plus 2. So if you multiply this by x plus 2, you will end up with this. Now multiply this by x plus 2. Plus. When you multiply this by x plus 2, you get 2. Now in this case, right, in this division, this is a divisor with which you divide. Sorry, divisor. This one is the answer, quotient. This is the remainder. Remainder. Here also the same. You use x plus, I mean, you divided this guy by x plus 2. So x plus 2 is the divisor. This is the answer, quotient. And 2 is the remainder. So if you write something like this, like a linear expression like this, like a line, not exactly linear, so you call it as the division algorithm. In fact, Euclid came up with this name. Still, we are using that. No matter in which format you have, you can have it in integers or you can have it in polynomials. It doesn't matter. That's called the division algorithm. Right? Okay. Now you take that down as well. And this is very important to us. And at the same time, this is very important, the long division of polynomials. You take that down completely.
They make one video post of video. Huh?
ඒකට මම උදේ ඉවරලා එන්න ඕනේ නැහැ ගෙදර.
නෑනේ.
ඉතින් ජැවලින්නේ දාන්නේ කොහොමද?
ඔව් ඒක ඉවරලා. ඒක මම
උදේ
ඕනේ.
ආයෙ ඇවිල්ලා යන්න ඕන.
අවශ්‍යන්නේ.
රිලේ
නෑ රිලේ කලින් තියෙනවා කිව්වා.
ෂුවර්?
හ්ම්.
ඉතින් නැත්තම්
So we'll do some long divisions now. Let's go through this example, and always I forgot one thing. Express the answer in the form of division algorithm. Right. I'll do 1 and 3. You divide it by x plus 2. When you do that, you take the leading term divided by x. So x cube over x, you get x squared. Once you get x squared, you multiply x cube plus 2x squared. Now subtract, you get 5x squared. Bring this guy down to this level. Now this is the leading term, 5x squared. You divide it by x, you get 5x. Now 5x times this 5x squared. 5x times 2 is 10x. Subtract, you get 4x. Bring that 10 down to this level. Now divide 4x by x, you get 4. So 4 times this, 4x, 4 times 2 is 8. Now you can write this in the form of division algorithm. How do you do that? This is equal to the product of these two plus 2. Divisor times quotient plus 2. It is like this. Let's take this example, 23 divided by 10. You get 2 as the answer, remainder is 3. So 23 is 10 times 2 plus 3. 20 plus 3, like that. Is equal to the product of these two. Right. Okay. We'll do the third, this one. There you need to deal with the negative numbers carefully. Okay. divided by x minus 3. So you divide the leading terms, x cube over x, you get x squared. When you multiply it by this one, you get x cube minus 3x squared. Subtract, you get minus 8 minus 3. Right? You have to subtract. Forget about x squared. I didn't write x squared. I just wrote the coefficients. So it will make this one positive. So 1 is negative, 1 is positive. Therefore, it's a subtraction. 8 minus 3, 5. However, the larger number is negative. Therefore, minus 5x squared. Bring this 19 down to this level. Divide this leading term by x. You get minus 5x. Now multiply. You get minus 5x squared plus 15x. Because minus 3 times minus 5 is 15. Subtract 4x. This gone. 19 minus 15 is 4. Now divide 4x by x. You get 4. Now 4 times x, 4x. 4 times minus 3, minus 12. Subtract. How do you subtract? Minus 8 minus 12. It will make this one positive. So you will end up with minus 8 plus 12. That is, I mean, you have two different signs, therefore subtract. Larger number is positive, therefore the answer is positive. 12 minus 8 is 4. So when you write this in the form of division algorithm, you have to write this is equal to the product of these two plus 4. So x cube minus 8x squared plus 19x minus 8 is equal to x minus 3 times x squared minus 5x plus 4. So the product of these two plus 4. Now, this is very similar, but you have to do it carefully when you do that. Now, I'll do the fifth one. All these are similar after that. X cube plus 4x squared plus 7x plus 8. 1478. Again, divide the leading terms. X cube divided by x squared. So it is like this. Two of them will go away, leaving x at the top. So you have x. Now, once you have x, you multiply x cube plus x squared plus 6. Subtract. This one will go away. This pair will go away. 4 minus 1 is 3. 3x squared. 7 minus 1 is 6. Bring this down to this level because we require 3 terms there. Now divide the leading terms. 3x squared minus, divide by x squared, you get 3. So 3 times this guy, 3x squared, 3 times x, 3x, 3 times 1 is 3. Subtract this 0, this 3x plus 5. Now, if you want to write this in terms of like division algorithm, in the form of the division algorithm, you can write this as a product of these two plus this. Three plus 3x plus 5. Okay, right. Okay, you do all of them. There are altogether 8. But I think time doesn't permit us to do that. We'll see what the time is. Okay. You go through this till 8:30. Then you take the break, dinner break. And then we can have 25-minute break. So I'll see you at 8:55. So you work with this till 8:30, then take a break. Then after that, we'll start the class again at 8:55. If it is not possible for you to do everything before 8:30, after coming back, we'll work on that. And then probably we can take 10 more minutes and then I'll do the discussion. And there are certain things, from the last four, there are certain important observations that we need to make. So we can do that afterwards. Huh? Okay. Now work till 8:30. You take this down. At least there are three. At the same time, you can do problem 2 and problem 4. And 5, do 5. And stop at that point. 1 through 5. Till 8:30, you can do this up to this point. 1, 2, copy this down as well. These 3 answers and second and the fourth. That will be enough. Then you can take the break. After coming back at 8:55, we can go through the other 3. Okay. You can copy this down.
දෙකේම දැන් මේ මාසේ මේ කොහොමද දීවලනේ තියෙන්නේ. දෙකේ ගිහින් බලන්න ඒ කොහොමද 3-4ක් කරන්න බෑනේ. අනිවාර්යෙන් හදන්න වෙනවනේ ඒක. දෙකක් තියාගෙන තියලා හදන්න ඕනේ. අද කරන්නේ නැහැ. තියන තව මේ චිකන් කන්නේ නැද්ද නං? බෑ. තියන්න කිව්වොත්. යන්න එපා.
Check one. We do 1 through 5, 1, 2, 3, 4, 5. Even though I have worked them out, you better copy that down. Do the second one and do the fourth one. You can do it on your own and copy this down as well. Hmm? So after, now it's like it's almost 8:30 now. Once you are done with the first 5, you take a break. Then I'll see you at 8:55. Right? Okay. I'll do the fourth one first. It's not a big deal to do the fourth one, but since there are some negative signs involved, probably you might have made a mistake. Now divide. When you divide the leading term, 6 cube over x is x squared, you multiply, subtract. Here you may run into problems. Here what you need is -5 minus -1. These two negative signs together will make it positive. Therefore, -1 plus 1, sorry, -5 plus 1 means they have opposite signs. Therefore, it's a subtraction. However, larger number is negative. Therefore, 5 minus 1 is 4. So it is -4. Bring this down. This is the leading term divided by x. You have -4x. Now multiply. -4x times x minus 4x squared. When you multiply these two, you get 4x. When you subtract, you get 3x. Bring this -1 in the same line to the same line. Now this is the leading term divided by x. You get 3. Multiply 3x minus 3. Again, you have the same problem. -1 minus -3. It will make this one positive. So 3 is larger. Larger one is positive. So 3 minus 1 is 2. So if you write this in the form of like in the format of division algorithm, you will end up with this. This is equal to the product of these two. Plus 2. Right. So if you have made any mistakes, get them corrected. Now we can move to 6, 7, and 8. 6 is very similar to the 5. Anyway, let me do 6. So I'll erase this part as well. Okay. So I'll do the 6th. So here, this is a polynomial we have. So 7. You divide it by x squared plus 6 plus 1. Probably you haven't had enough time to do this. I'll give you 5 more minutes. You do this, and then I'll do them for you. Okay. So we'll, anyway, I'll do this for you. So again, in the sixth one, x cube should be divided by x squared. You have to take the leading terms and divide them. So x cube over x squared is x. Now multiply x cube. When you multiply these two, you get x squared. Here you get x. When you subtract, this will be gone. 3x squared minus x squared, you get 2x squared. 4x minus 6, 3x plus 7. Now divide this by x squared. So divide these two, you get 2. Multiply 2 times this, 2x squared, 2 times x, 2x. 2 times 1, 2. So when you subtract, you get x plus 5. Now you can write this in the format of the division algorithm. So you can write this one as the product of these two. Plus x plus 5. I'll do the 7th. In the 7th, this is what you have. X cube plus 2x squared plus 2x plus 5. Right. Now divide the x cube by x squared. You get x. Now multiply x cube plus 6 squared plus 6. Subtract. When you subtract this one, you get x squared. Here you get x. Here you get 5. Now divide x squared by x squared, you get 1. Now multiply 1 times this, 1 times x, 1 times 1. So when you subtract, you will end up with 0, 0, and 5 minus 1 is 4. So if you write this in the same format, you will end up with this one. This is equal to the product of these two, plus 4. 4 is the remainder. Now we'll take the last one. Then after doing the last one, we can make some important observations. 2 observations. That's the 8th one. Okay. Now again, divide the leading term of this one by the leading term of the divisor. X cube over x squared, x. Now multiply and subtract it from that one. X times x squared, you get x cube. X times x, you get x squared. X times 1, you get x. Now subtract. This is gone. This pair is gone. However, this is x. This will give you x squared. This pair will give you x plus 1. Now again, you do the same thing. Divide the leading term of what you have here by this one, so which is 1. Now 1 times this, x squared, 1 times x, x, 1 times 1. You get 0 there. So if you write this in terms of like in the form of the the division algorithm, you will end up with this. This is equal to the product of these two plus 0. Product of these two plus 0. So plus 0 is not necessary to be written there. So you can stop it at this point. Right? Okay. So if you have any, if you have made any mistakes, please correct them. Right. Now, in these four cases, you got remainders like this. Here the remainder was in the first case was 2. Here the remainder was 5. Here the remainder was like 4. Here the remainder was 2. So in these four cases, the remainders were just numbers. That means what? They were the polynomials of degree 0. But here the divisor has the degree of, divisor, all the divisors in the first four cases are of degree 1. So divisor has degree 1, remainder, the remainder, sorry. So the remainders have degree 0. Remainders are of degree 0. Divisors are of degree 1. 1, 0. 1 less. This 1, this is 0. Degrees, I mean. Right? The largest power of x appearing in that expression. Here you have 2 means like 2 times x to the power 0. So all these are 0 degree polynomials, but the divisors are first degree polynomials. So 1 and 0. 1, 0. Now here, in these four cases, I have erased the sixth one. Fifth one, the remainder was, look, 3x plus 5. In the eighth one, the remainder was 0. Here it is 4, right? In seventh one, it is 4. So remainders were like this, 4. This is 0. Here it is x plus 5. In the sixth one, let me see what it is. Hold on. X plus 5. That is 3x plus 5. This is x plus 5. You can see that here the degree is 2, here the degree is 1. 2, 1. Here the degree is 2. In this case, the remainder, in the case of the remainder, the degree is 0. However, the largest possible degree you get is 1 less than this one. When it is degree 2, you get degree 1 as the remainder. The largest possible degree should be 1. You have the same phenomena with the numbers as well. Say, for example, when you divide 10 by 3, you get 3 as the answer, 1 is the remainder. When you divide 11 by 3, you get 3 as the answer, while the remainder is 2. When you increase this by 1, when you divide it by 3, you get 4, and the remainder will be 0. So we have all cases here. Like when remainder is 0, you can say that you can write this 12 as 3 times 4. So 3 becomes a factor of 12. If the remainder is 0, 3 becomes a factor. So same thing is there in the 8th case. When this is 0, when the remainder is 0, you can write this one like the product of these two. So in that case, you can say x squared plus x plus 1 is a factor of this. Now, if you write 12 is equal to 3 plus 4, sorry, 3 times 4, 3 is a factor of 12. 3 is factor of. So here, that happens when the remainder is 0. However, when you divide some number by 3, whole number by 3, the largest possible remainder is 2. You cannot have something more than 2, because if you have something more than 2, you can divide it by 3. Like if you have 3 or 4 or 5, you can divide it by 3. So largest possible remainder is 2. When the device is 3, it is exactly 1 less. 3, 2. So here you have the same pattern, but not exactly this. I mean, similar pattern, not exactly the same. Here you cannot say a value to this one. However, if you take the degree, like degree of the degree of the device is 2. In all those 4 cases, degree of the device is 2. Degree, the power. So large, I mean, you can have even 0 there. You can have 4. 4 means a 0th degree polynomial. 4 times 6 to the power 0. But you can, at most, the largest possible degree you have for the remainder is 1. 3x, x. So when this is 2, it is 1. 1 less than that. Like same thing. When the device is 3, the largest possible value for the remainder is 2. 1 less. Here, when the degree of the device is 2, the largest possible power you get for the remainder is 1. 1 less. Here, when it is 1, like first power, for the remainder you get a constant. So there are 2 things that you need to observe. The largest possible degree, right? Largest possible degree of the remainder is 1 less than that of the divisor. That's one thing. Second is when you get 0 as the remainder, divisor or 3 is a factor of this number. Same is true for the polynomials. So let's make those 2 observations. And let's take down this note. There are two things that you need to note. First one. Completely divides fx. That means something like this, huh? That means the remainder is 0. You can write fx. We have, right? Fx is equal to the product of these 2 plus 0. So that means, or that is, x minus a is a factor of fx. Because if you write fx as the product of these two, this is the factor of fx. That's the first thing we need to note. Second, the largest possible degree of the remainder. The remainder is one less than the degree of, that of means the degree of the divisor. Let me tell you what this is. Huh? Say you divide this by x minus a. You get something here. Some polynomial, that's a divisor, that's a quotient. However, what I am talking about is the remainder. Remainder is one, the degree of the remainder is one less than this. Here device is one, sorry, not the divisor. The degree of the device is one, degree of the remainder is zero, constant. When you have something like this, you can have some quotient. We don't know what it is. If you don't know this, we don't know what this is. However, we can write something about the remainder. Look at this. Look at this, right? Now, here we have 3x plus 5. Here we have 0. If you want to cover all of them under one format, how do you cover everything? All four. You can do it like this. If you take this as ax plus b, if you compare it with this one, a is 3, b is 5. Here, a is 1, b is 5. In the third case, a is 0, b is 4. In the fourth case, both a and b are zeros. So if you assume this format, you can cover all possible remainders. So you can do it like this. Now, when the device has the degree 2, you can assume that it has the remainder of these 4. Why? Because the degree of the device is 1 greater than that one. Or in other words, the degree of the numerator, degree of the remainder, this is the remainder, is 1 less than that of the divisor. That's the largest possible degree anyway. So if you assume that this is A or something, or R or something, it doesn't work. Why? Take this one for example. If you assume this as R, these two are covered, that's fine. However, here, how can you model this one? You cannot. Therefore, in general, you have to, if you don't know what the remainder is, you have to cover all possibilities. You have to go for the largest possible degree. So the largest possible degree of the remainder is 1. The degree of the device is 2. 1, 2. 1 less. Here, degree of the device is 1. Degree of the remainder is 0. 1 less. Here it is 1 less. Okay, you take this down. These are the important observations that we made. The next thing that we need to do is the remainder theorem. However, if we do remainder theorem, we need some time to go through some examples. Just to make you understand it a little better. However, the time doesn't permit us to do that because we have only 25 minutes left. I mean, if I do remainder theorem, it might take nearly 10 minutes to 15, 12 minutes with the proof and everything. So with that, I think we will be stranded. Like we will end up with no time to do some examples. We don't, I mean, the time left wouldn't be sufficient enough. Therefore, we'll do it like this. We can start remainder theorem next time. That's the second chapter. This was the first chapter, Introduction to Polynomials. In the second chapter, we go through remainder theorem and together with examples. Like probably in the second section, we can do something similar to examination type questions. And but to get some like solid background of remainder theorem, we need some time. We need to spend with we need to spend some time doing those problems. So the time we have, time left today is not enough. It's not sufficient. So we can do it next time. And the tutorial will be sent to you next week. Like we'll send them tomorrow. Probably you will receive them by probably 2 days after that, 4 days. Yeah, 3 to anyway, within 3 to 4 days, right? Before that, you will receive it. So we can, since, I mean, when you have the tutorial with, I mean, at your disposal, it will be easier for us. Therefore, once you get the tutorial, we can do the problems a little faster. Otherwise, we have to copy, I mean, write all the problems with wordings and stuff like that. So next day, I'll start remainder theorem and we'll do some simple examples first, and then we can start doing examples similar to the past paper questions. Even though we are going to wind up little early today, I ended up where I want to be, right? කියන්නේ මෙතන තාමට ඉවර කරන්න ඕනි. මීට වඩා දැන් තව කරොත් remainder theorem එක ඒකට examples කරන්න වෙලා වුණා. ඒකට වෙලා මදි වගේ. හරි. ඒක එකක් දෙයක් කරලා වැඩක් නැහැ. ඒක remainder theorem එකත් එක්ක examples ගොඩක් කරන්න ඕන හින්දා ඒක අපි next week කරමු. ටියුට් එකත් කූරී කරනවා හෙට. ඔයගොල්ලන්ට දවස් කීපයකින් හම්බ වෙනවා. ඒතර next week ඔයගොල්ලන්ට ටියුට් එක තියෙනවා ඇති. ඒකෝර අපිට මේ problems ටික ගේමක් නේද කරන්න පුළුවන්. මේකෙම මේ ඒතර අතේ ටියුට් එකේ තියෙද්දි copy කරන්න ඕනේ නැහැ problem එක. නැත්නම් මට problems list එක හැමතිස්සෙම ලියන්න වෙනවා. ඒතර ඔයගොල්ලන්ට වෙලාව අපරාධයි. Right? So because of that, we can wind up at this point. And I'll see you next week. And I'm really sorry that I had to cancel last time's class because I was terribly sick at that time. I had classes from like 8 to 2:30 and then through 3 to 6. Right? I was so scheduled from 7 to 10. So I was totally like extremely, I'm exhausted by that time. Therefore, I had to visit a doctor. Because of that, I couldn't cancel it, and I didn't recover. Even I recovered just yesterday. So we didn't have that extra class also. Anyway, but with this phase, I finished. I mean, I ended up with where I want to be. So we can wind up at this point, and I'll see you next week. So next week, we'll start with remainder theorem. Right? Okay. Thank you.